I'm here on behalf of Marcel because he couldn't be here and to present his and our or my work. And yeah, for the next generation BigBrain, let's start with the current generation BigBrain and have a quick look at that. I think you've already seen this one quite some times. And yeah, it's at 20 micron resolution. And it's very nice, but for the next generation, we have got a little wish list. So first of all, we would like to go from optical densities to actual real cell densities. So we can count them, look at the shapes. In addition, we would like to extract 1 micron planes at arbitrary cutting angles. So we can do brain mapping on those. And the last one, as a nice bonus, we would like to improve on the reconstruction. And all these things we would like in an automated fashion to reduce manual labor. So this video here is the first 1 micron reconstruction, 3D reconstruction. It's available on eBrains. I will show you the slide later where you can get it. And as you can see, we see a lot more than in 20 micron. We can see the cells, individual cells. We can see the blood vessels very clearly. So this would enable us to get better cell densities. The next video shows the difference in reconstruction. At best, you look on the lower right, where you can see that 1 micron reconstruction achieves much more sensible results in the shape of the cortex. And this reconstruction is available on eBrains. As you can see here, under the DOI, there's 2 volumes available, in V1 and V2. And yeah, you can jump right into that later. Now for some methodology, how did we achieve this? We used something called microstructure guided reconstruction. The basic idea is we have a stack of images, of 2D images. We detect some microstructure. In the image here, it's blood vessels. For our results, we used truncated cells. We match them, and then we use some alignment to align the images together. In the release, we used a section-by-section approach with linear registrations. So we have a stack of images, and let's assume the first image is already in good shape. Then we calculate and define a linear transformation between the first and the second image and apply it to the second image. And to get the reconstructed results, after that, we calculate a affine transformation between the second and third image and apply this affine transformation and the previous affine transformation to the third image. So we build up affine transformations one after the other to reconstruct one image after the other to the stack. So for a stack with n images, the last image would have n-1 affine transformations. Now this is very nice and a quite easy approach, but it has some limitations. Especially it's limited to small volumes. One problem is that it cannot model nonlinear deformations. As we're using a linear transformation model, that's quite clearly. And as we can see in the example here, when we have 2 hemispheres moving at different directions, having different deformations, this doesn't work. In addition, this section-by-section approach tends to propagate errors through the stack. As we apply one affine transformation after the other, all errors build up over time. Okay, now to the first problem, the nonlinear deformations. It's quite easy solution. We just use nonlinear transformations. In our case, polyaffine transformations. And as you can see, the results look much better. We can deform 2 hemispheres at the same time, and we can deform all nonlinear deformation in 1 hemisphere as well. And onto the section by section or the error propagation problem. Instead of doing a section by section approach, one after the other, we chose to optimize all parameters simultaneously. So we have a stack of images, and we determine in the first step the optimal position of each cell. So we get the matching information correctly, and we don't do too much things to the image. And in a second step, we use our polyfill transformations to model exactly this deformation. So remove the section by section approach, so there's no error propagation through the stack anymore. And when we compare these results, we can see that it's actually really working. So these are cross sections of 300 sections. One time linear reconstructed, one time nonlinear reconstructed. In the red circles, you can see on the one hand, the outline of the stack looks quite jagged. It's very irregular. And you can also see some so-called banana effect, so the straighting of the brain. And below, we see the nonlinear result, and we can see there's a smooth curvature. There's no banana effect. This looks really fine. Now to a small movie showing some more cross sections, panning through the 300 sections. And we can see that this reconstruction quality is achieved all over the stack. Finally, we can also see that the truncated cells we use for reconstruction are actually aligned after the registration process. So this enables us to count the cells more precisely because we can see which cells are matching up together. You can see them in the upper right cross section, especially right in the middle. There's one that matches up pretty nicely. Yeah, I think I was very quick. Yeah, I was very quick. Thank you for your attention, and thanks for all the people working on this. And I think we have time for some questions.